So welcome everybody to this week's OWL seminar, and it's my pleasure to welcome Andrew Pitts. But before I get started, just a little bit of housekeeping. So the talk is recorded. You're absolutely very welcome to ask questions during the talk. We try to encourage that. So if there is a question, you can either write to me in the chat or you can put your hand up and I'll be able to see that in the participants menu. And you can find also that ability to raise your hand in that menu, or I think it might be under the reactions button. Yes. After the talk, we'll have some questions which will also be recorded. So if you want to ask a question, you'll be recorded. At some point, we'll turn the recording off, and you're welcome to also stay behind after the talk and ask additional questions and discuss things with Andy. And I think that without further ado, I'll hand over to Andy Pitts. Please go ahead.
Thank you very much, Pavel. So thank you for inviting me to give this talk. So I'm going to be talking about some recent work I've been doing with Sean Steenkamp, who's a PhD student in Cambridge. And so this is, so the title is Constructive Initial Algebra Semantics, and this is a talk in the OWL seminar, right? So OWLs is about logic and semantics. So the logic that I'm going to be talking about in this talk is constructive logic of various kinds. And the semantics is going to be a bit of category theory for computer science that I suppose, I think if we did a poll, probably most people would agree is one of the sort of fairly straightforward and quite fundamental things that category theory has given to semantics, namely just the simple notion of an initial algebra for an endofunctor. And I expect you probably all know what I mean by that, but let me begin just by giving the definition so that we're all on the same slide, as it were. So let's suppose that we have some category C, and we have a functor from C to itself. So one says that an algebra for that functor, an F algebra, is just an object of the category X, equipped with a morphism from f of X back down to X. And so an initial such thing, there's an obvious notion of morphism of such algebras. And so we'd be talking about the initial object in that category. So it is a particular algebra. And if you've got any other one, then there's a unique algebra morphism from the initial one to it. So that unique morphism was christened, I think, by some functional programmers, the catamorphism associated with the algebra structure H. It's not a term that I particularly like, but some people are familiar with it. So this is very straightforward notion. And the reason it's of interest, of course, is because depending on how you choose your category C and your endofunctor F, then if the thing does have an initial algebra, it very often gives you all sorts of interesting structure to do with inductive and dually, for opposite categories, co-inductive things. And the catamorphism would be giving you the semantics of various kinds of recursion schemes or dually co-recursion schemes. And I'm not going to recall any of that except for one specific example, because we'll need to use that one example a bit later in this talk. So a W type is an example of an initial algebra for an endofunctor. Let's just do it in the category of sets. So if I start with a so-called container, so that's specified by a set A and an A-indexed family of sets B. Okay, we can associate with that a functor from sets to sets, a so-called polynomial endofunctor determined by that container. So what the functor does at X is just to give this disjoint union of exponentials. So concretely, f of X consists of pairs, namely an element of the set A and a function f from the associated set BA back to X. And that does indeed have an initial algebra, and one of its manifestations up to isomorphism is the set of well-founded algebraic terms if we think of the container as giving us a possibly infinitary algebraic signature. So the A would be naming operation symbols. So I'll write sup sub A for the operation symbol associated with A. I don't know why I do that. It's kind of traditional, but it's not because this is going to be any kind of least upper bound or anything like that. So each operation symbol has an arity, and that's what the set BA gives us. So that's the number of arguments that that operation can accept. And if the sets BA were all finite, then we'd be talking about an ordinary finite tree signature. But in general, you might want to allow a whole set of arguments. So a typical term in this set of well-founded terms, a typical term T is going to be of the form an operator applied to recursively a family of terms indexed by the arity associated to that operator. And everything that you get like that built up is what the W type associated with the container AB is. And that's the underlying set of the initial algebra for the polynomial endofunctor. And we'll need W types later on in this talk. So going back to the general case where we've got some arbitrary category C and some arbitrary endofunctor, when do we know whether or not there is an initial algebra? So there's a classical construction that works with suitable assumptions about the category having enough colimits. So if we assume that our category has all small colimits, so in particular colimits indexed by the elements of some ordinal number with its usual order. So in particular, it's got an initial object, which I'll write as 0. We can iterate starting at the initial object transfinitely. In other words, iterate over all the ordinals, build up a series of objects, which I'll write as F alpha of 0. So that's the alpha iterate of the endofunctor starting at the initial object 0. So at 0, it's 0, and at a successor, something of the form beta plus, it would be F applied to the thing that you've already got. And at a limit ordinal, you just take the colimit of the preceding things. And of course, for that to make sense, it's because we've been at the same time building up a sequence of morphisms from one stage to the next. So at the start, that's uniquely determined because 0 is an initial object. And at a successor stage, you just apply the functor to the previous thing, and at limits you use the universal property of the colimit to induce what the I morphism is for lambda. Okay, so we can build up such a sequence, and a very long time ago, Giriadamek noticed that the fact that's true for monotone functions on complete lattices can be categorified, if you want to put it that way. And if it's the case that our endofunctor preserves colimits for some limit ordinal kappa, okay, which is just exactly to say that one of these transfer morphisms I sub kappa for kappa limit ordinal is an isomorphism, then actually that's the iterate at kappa is giving us the initial algebra. And the algebra structure is just the inverse of the transfer I sub kappa. So that's a very old theorem, and now it's true classically. I said it's a classical construction. I suppose it's a slight pun in the sense that it's an old construction, but it's also one that relies in various ways on the fact that you're doing this in classical logic. I mean, one way is, of course, that the theory of ordinals, to get most of its properties, an ordinal is in particular a totally ordered set, and we want to be able to know whether an ordinal is either 0 or a successor or a limit ordinal, and there's the only 3 possibilities. We use the law of excluded middle all over the place in order to develop the classical theory of ordinals, and in particular in defining that transfinite sequence of objects. So that's one sense in which this theorem is a classical theorem. And the other sense is that there won't be very many functors that preserve colimits of shape kappa classically without in general some use of a choice principle. So, I mean, if we look, say, when the category C is the category of classical sets, so sets in Zermelo-Fraenkel set theory with the axiom of choice, okay, and we look at the example that we had of polynomial endofunctors whose initial algebras were those W types, right? Then when does a polynomial endofunctor preserve kappa-sized colimits? Well, if you take kappa big enough, it will, right? And big enough means that you remember that the container is the signature. We've got some operation symbols indexed by the elements of A, and we've got an arity B of A for each little a in capital A. And if we take the ordinal big enough so that any arity indexed family of things less than kappa has an upper bound that's still less than kappa, then that's enough to be able to prove that the associated polynomial endofunctor preserves kappa colimits, and hence we can apply Adamek's theorem to construct the initial algebra for the functor. And that's can be done using the axiom of choice, because if you think about it, what are colimits in the category of sets? They are particular quotients by an equivalence relation of a disjoint union of things. I mean, if we have some diagram, then we form the colimit in the time-honored fashion. So if we're trying to see that the functor f preserves colimits, we'd be in the business of having a function from B of A into the colimit and trying to produce out of it something in the colimit of the diagram of functions. And how could we do that? Well, I mean, if we've got such an f, it's landing us in this quotient set. So we could use the axiom of choice to pick a representative for each equivalence class as little b ranges over the arity B of A. So use AC to do that, and then pick an ordinal that's an upper bound for all the places that we've landed in, and that will still be less than kappa because of the assumption, and then that will give us an alpha that we can land in. That will give us one function, as it were, from B of A into stage alpha, and then the representative of that will be the way of turning things like this into things like that. And then it's but a small step from that to see that we've actually got an isomorphism when you're applying f to this colimit. So you can certainly use the axiom of choice to prove that some endofunctors do preserve enough colimits to give us things. So I'm interested in getting a constructive version of that theorem of Adamek. So one that if you want to put it in a somewhat negative way, doesn't use the law of excluded middle, doesn't use the axiom of choice. I mean, that's a rather sort of backhanded way of saying what constructivism is about. And I thought before telling you about that, it's beholden upon me to explain why it is that you should bother. Why isn't the classical theorem satisfactory? Okay, and of course there are lots of different reasons why one might be interested in constructive versions of this theorem, and of course of many other things. I mean, it might be that you have philosophical objections to things like the axiom of choice or the law of excluded middle. It might well be, and since probably many of you do computer science, that you're interested in computational content of things. And generally speaking, a constructive treatment will give us more computational insight into something. I mean that in a slightly informal sense. If one succeeds in finding a constructive explanation of some particular bit of mathematics, it very often means that you get a more concrete and algorithmic way of understanding what's going on. So these are certainly perfectly good motivations. But actually for this work, my motivation was rather utilitarian, in fact, and neither of those. It's that the internal language, so-called, of many sorts of different category is naturally not classical, is constructive in various ways. And a prime example of that is the internal logic of elementary toposes. So a topos is a simple enough category theoretic concept. I mean, a topos is a category with finite limits and exponentials, so it's a Cartesian closed category, and it has a sub-object classifier, so it has a generic monomorphism from which every other monomorphism appears uniquely by pullback. So that doesn't take much to say what an elementary topos is. It's a very compact definition. But the consequences of those properties are huge and diverse, and many books in many volumes have been written about the things that follow from that simple definition. And one of the reasons for that is because we know that elementary toposes correspond in a sort of Bill-Lorvier style to particular theories in intuitionistic higher order logic with extensionality to begin with. So that which is whilst it's intuitionistic, it's a higher order logic. So it's a fairly expressive formalism. And better still, for the kind of things that I'm interested in, if you allow your toposes to have natural number objects, so have infinity, and actually, in fact, importantly, to have enough internal universes as well, then you can take some form of extensional Martin-Löf type theory with at the bottom a little impredicative universe of propositions as the internal language. The point is that everything that you can say in that kind of logic can be interpreted in one of these toposes, and that can be a very nice way of constructing something that, if you just did it purely category theoretically, could be quite complicated to describe in a diagram chasing way. So a recent example of that, which is kind of, I think, in the back of my head for why I'm interested in this at the moment, is I did some work with various people a few years ago trying to understand the so-called cubicle sets model of univalent foundations. So that was a construction done in a particular pre-sheaf topos, so a particular kind of elementary topos. And the construction is of the model of homotopy type theory, univalent foundations, that's done there. Involves some quite elaborate things to do with various notions of fibration and co-fibration, so the sort of Quillen model structure kind of thing that one has there. And I found it hugely helpful to be able to describe what was going on using the language of type theory itself as the descriptive language to describe what the constructions were. And if you're interested, you can see that kind of thing in these two papers. It's fortunately or unfortunately not quite true to say that it's just extensional Martin-Löf type theory with universes. So to get the sort of internal description of the univalent universe, we actually have to slip into a kind of modal type theory, which makes a distinction between global and local constructs, but never mind that in this talk. So there is at least in my head, a desire to know the answer to this question. Is there a version of the theorem of Adamek that I just described to you, the one in classical logic, that works at the level of any topos with natural number object and universes? And that's the question I'd like to address in the rest of this talk, and give you at least one answer to that question. Okay, so I'm gonna do this in two steps. Okay, so the first step is I want to eliminate this use of law of excluded middle, if you like, or the disjunction between whether an ordinal is zero or successor or limit. So we can get around that in forming an iteration by using a slightly different way of doing the iteration. So I don't know whether an inflationary iteration is quite the right term. It's the one I'm using at the moment. If somebody has a suggestion for a better terminology, then we're open to suggestions. But what I'm going to do is do an indexed family of objects. So we're in a category C, and we've got an endofunctor F from C to C, and we're forming a sequence of objects, and I'll call those objects mu alpha F. And instead of doing this, okay, what I'm going to do at each stage alpha is take the things that we've already built up, mu beta for beta less than alpha, take F of them, and then take the colimit. So you could do that with ordinals classically, but actually it doesn't require very much of the indexing things in order to make sense of what's in this box here. So what will alpha range over? I'm going to let them range over things I'll call sizes. So a size will be a set equipped with a binary relation, which is transitive. So it's in that sense an order. Directed. So by directed, I mean that first of all, the set is inhabited, speaking constructively. So not non-empty, but inhabited. And you have an upper bound with respect to this transitive relation less than for any pair of things. So given a pair of things, we can find a third thing which is above both of them. And then crucially, we want it to be well-founded. So if I've got some subset of my set of sizes, and I want to prove that everything is in that subset, it's enough to show that if you can show that whenever all the things preceding alpha are in S, then alpha has to be in S. If you can do that for any alpha, then that's enough to show that S contains every alpha. So that's one of the ways of stating in a constructive way what non-constructively you would say in terms of not having infinite descending chains, but that's not a very good way of putting it if you're working in constructive logic, and this is a good way of doing it. So that's what I mean by a size, a well-founded transitive and directed relation on some set of things, okay? And we can make this kind of iteration using any notion of size we like. So I've stated this as a lemma. So we've got our category C. We need to be able to form colimits at each stage. So let's just assume that C has small colimits. I mean, that's more than you need, but it's good enough. And we've got some endofunctor from it to itself, and we've got some size. Then we can form this sequence of objects indexed by the elements of the size so that at each side alpha, mu alpha is the colimit of the F of the things that we got for strictly smaller sizes beta. And you just need transitivity and well-foundedness of the relation less than on this set kappa in order to construct this by well-founded recursion on the elements of the size. And having done that construction, then it's actually not too difficult. So it's not a very deep theorem that if the functor preserves colimits of size kappa for this notion of size, then the initial algebra is given by taking that colimit over all sizes of the things built up in that way. So I won't go through the proof of that, but I just say that it's you don't need directedness of the notion of size in order to prove the lemma, but I think you do need it in order to prove the theorem. And one thing about directedness, I just flick back to the definition. You can apply this when alpha and alpha prime are the same thing alpha, which might sound like a silly thing to do, but part of directedness is to say that for every alpha there exists something which is strictly bigger than it in the set of sizes. So in other words, we do have a sort of successor operation whenever we've got a notion of size. So in that sense, a size is playing the role of a limit ordinal in this constructive setting. Okay, so that's good. So we have a constructive version of that theorem of Adamek by changing to this constructively acceptable notion of size rather than using ordinals, and it works not too dissimilarly from how it worked before. But that's all very well. But of course, there may not be constructively many functors that preserve colimits of some size. So that's the other thing that we have to worry about in step 2 is does that theorem actually give us anything interesting? Are there many such sizes and endofunctors? Well, okay, so if you think back to the classical situation, right, we saw, for example, that the polynomial endofunctor preserved colimits of a certain ordinal size because the ordinal had the property that it was closed under arity-sized families. You could find upper bounds for arity-sized families within that ordinal. So it suggests that for each signature, in other words, each container, we need to be able to find a size kappa which is big enough in the sense that it has up bounds not just for finite sets of things, but for any possibly infinitary arity indexed family of things. And the interesting thing is that actually you can do that. So I think what I've told you so far, I think, interesting though it might be, is maybe not very surprising, but the next bit was a surprise to me, that one could find enough sizes in this rather straightforward sense. Okay, and so there's a theorem that says that actually, in fact, for any signature, you can construct a sigma filter size. So if sigma is our signature, so I'd say a size is sigma filtered if it's got upper bounds for every arity indexed family using the arities from the signature. And the fact is that we can find enough such sizes, okay? And the proof I'll show you uses W types, which is why I mentioned them to begin with, and a certain well-founded ordering on them, not the one you'd first think of, I think, but the one that Paul Taylor came up with some time ago. So you remember our W type, it's the set of algebraic terms over this possibly infinitary signature, okay? And if I told you put a well-founded ordering on that W type, I think you would probably come up with the one which is inductively defined like this. In other words, some term is strictly less than a term of this form if it's strictly less than one of the components, one of the arguments to the operator, so one of the FBs that you're forming when you're forming this term sub of F. Now that's not good enough for what we need, because that doesn't make that an upper bound with respect to the strict well-founded ordering for this family of elements. So in a sense, it's not long enough or fat enough or plump enough, I suppose. That's where maybe the word plump comes from. We need something else, and Paul Taylor supplied to something else with, I think, it's a very clever definition that's actually rather hard to understand the first time you see it. So I don't expect probably in this pass the implications will maybe sink in. We can define a different sort of relation between infinitary terms. It's mutually inductively defined with a pre-order. So there's a less than or equal to, and there's a strict less than. And inductively, a term is strictly less than something of the form sup f if t is less than or equal to one of the components fb. And on the other hand, a term sup f is less than or equal to t, flipping over the roles, if all of its components are strictly less than t. Well, there's a definition. You have to think a bit to see that actually strict less than in that definition, it's always transitive, it's always well-founded. And actually, we always now have that one component FB of the sup is strictly less than the sup, because we've got this here, and less than or equal turns out to be reflexive. So f of b is less than or equal to itself, and therefore f of b is strictly less than sup f. So this is giving us a way of having a well-founded order on the algebraic terms, which is plump enough. And if we've got an arity which is got at least one thing in it, it's got no things in it. So if we have an arity which is empty, in other words, our operation symbol is a constant, then the W type will be inhabited. And if we have an arity which is a binary operation, so where the arity is 2, then the ordering will be directed, because we'll be able to take upper bounds with respect to that operation symbol to get upper bounds for pairs of things. So as long as those conditions are true, then the W type equipped with its plump strict less than ordering is a size in the sense that I've been talking about. So to prove this theorem, okay, if you give me a signature, I won't take the W type on that signature. I'll just add a little bit to it to ensure I've got directingness, right? So I'll take the operators to be the operators I had before, plus an operator of arity 0, an operator of arity 2. So there's a typo. No, there's not a typo, right? Yeah. So the arity B prime of something I had before is what it was before, and the arity of 0 is the empty set, and the arity of 2 is 1 plus 1. So that will give me something which is directed and has upper bounds for arity indexed families for the original signature. And so that will give me a size which is sigma filtered. So let's call an endofunctor between co-complete categories in some constructive setting, say in an elementary topos with natural number objects and universes. Well, I'll say it's sized if it preserves co-limits of any sigma filtered size. So whenever you have a size which is big enough in the sense that it has upper bounds for arities coming from the signature sigma, so a sigma filtered size, I would like F to preserve co-limits over that size. And if it does, then I'll, and that's true for some signature sigma, then I'll say that F is a sized functor. So it's not too hard to see that constant valued functors are sized, and taking the quotient, if you had a pair of natural transformations between two sized functors and you formed a coequalizer, then because coequalizers are going to commute with other colimits, we'll get another thing which is sized. That does require just a little lemma to see that if we've got two sizes, I can find a size bigger than each of them for a suitable notion of bigness, which would just mean sigma filteredness implies sigma filteredness, as it were. So our class of sized functors contains constant things. It's closed under quotients, which is nice. It's closed under index products for any set in one of the universes in this topos. But what about having it closed under index products as well? So if you remember classically with our W types, that was where I snuck in a use of the axiom of choice in order to see that something was preserving ordinal limits of a suitable size. So I think preservation, the product of some possibly infinitary collection of sized functors, again being sized, is not going to be true without some kind of choice principle. Okay, but we want to avoid the axiom of choice. What we found is that the choice principle whisk is enough. And I'll explain what whisk is and also why you shouldn't feel too unhappy about assuming that it's true. Let me first of all tell you what it is. So you remember the axiom of choice. I mean, one way of saying the axiom of choice is if you've got a set A and you've got a surjection from B to A, then that surjection splits. Choice tells us that we can find a map back from A to B, which composed with it gives you the identity. So what the axiom whisk is like that, but whisk, by the way, stands for weakly initial set of covers. So instead of assuming that we've just got this one thing, we'll assume, given the set A, that there's an indexed family of surjections, so that if you've got any surjection to A, then you can find one of the things in the family through which you can factor through the given thing. So in other words, this family is weakly initial. It's a weakly initial family of surjections to A. Any surjection to A you can get from some member of the family to it. So this is an axiom that I think Thomas Streicher introduced under a different name. Independently, I think Palmgren and Moerdijk introduced it, and then Benno van der Berg and Moerdijk wrote papers about it under the name of the axiom of multiple choice. So I'm using Wikipedia or NLab's name for it, which I think I prefer because it's more descriptive in a sense. Whisk, well, weakly initial set of covers. Now, it's an axiom of choice, clearly, because it looks very not, just looking at it cold, it doesn't look too different from the axiom of choice, right? But the interesting thing about it is that, and it's something that Van den Berg and Moerdijk proved, is that, well, yeah, certainly classical sets satisfies it, because the axiom of choice implies whisk. You can just take the family to be a singleton family just containing the identity on A. But if you've got a topos that does happen to satisfy whisk, like classical sets, and you do, say, a pre-sheaf, sheaf, or realizability topos construction to get another topos out of that topos, then whisk is conserved. So actually, in fact, pretty much all the toposes that we're interested in when we're, say, building models of type theory do satisfy whisk, if you're willing, as it were, to come in the outset from a classical point of view, where you've got the axiom of choice, or at least somewhere where you start with a whisk. Not every topos, not every elementary topos satisfies whisk, and this paper of Roberts gives an example of one that doesn't. But the message is that whilst it is a choice principle, it's what some people would call constructively acceptable. I think you have to take that maybe with a pinch of salt. But what it's meant is that it's satisfied in a very wide range of places. So from this utilitarian point of view of constructivity, we want to use it in the internal language of various toposes to do stuff. Then whisk is there in most of the toposes that we're interested in, so we might as well use it. And the theorem that we prove is that you can use it. So if you've got a family of sized endofunctors on some universe in an elementary topos satisfying whisk, and you take their product, okay, then you can use this whisk principle to prove that that is again another sized endofunctor. So, and therefore also that has initial algebra, because so we get, to summarize, quite a, if you're prepared to accept whisk in your setting, a class of functors closed under sigma and pi and quotients and constant functors, and so that's actually, and you can do it parametrically in the sense that you can take initial algebras in one argument while keeping the other fixed to get a functor which you then take an initial algebra of. So we get a very rich collection of things that have initial algebras. So an example, I mean, we already know that polynomial endofunctors on toposes with natural number objects have initial algebras, but you don't need the axiom of choice to prove that. But I don't think that we knew before that, for example, symmetric containers in Gilterud's sense have initial algebras in that constructive setting. So a symmetric container would be where instead of having arities that are just sets, you have arities with some sort of symmetry on them, and you only consider algebras that are invariant with respect to mixing up the arguments of the operator with respect to the symmetries. So I mean, one way of putting that is that we could take the, instead of having a set A of operators, we could have a groupoid of operators, and then the arities would be a functor from groupoids into say in some universe in one of our toposes. So then the symmetric polynomial functor associated with that is going to be given by not the sigma of the function spaces, but the colimit as G ranges over the elements of the groupoid. So that's a quotient. It's a colimit, right? Remember, is a quotient of a sigma. So that's exactly something where, as long as we've got whisk around, we know each of these things is sized, and so we'll know that this thing is sized, and so we can take its initial algebra. And specific examples would be, you could do infinite tree multisets that way, or you could do infinite unordered branching trees. I think Torsten is raising his hand, is that right? Or maybe not. I will continue. So there are examples of new things that we get in this way. So what have I shown you? I would say that the plumply ordered W types, at least where you've got the setting of this whisk axiom around, seem to be quite an interesting constructive substitute for classical ordinal numbers, at least for some purposes. And Marcelo Fiore and Sean and I have a paper that's in being refereed at the moment, that is on Archive, where we use the same ideas. We don't, the results are not a corollary of what I've shown you here as far as I can see, but they use the same techniques to get so-called QW types, so a mixing of quotients and W types together that encode many kinds of quotient inductive types. So that would be a further example of this kind of technique. What we haven't thought about, but I think would be interesting to think about, is the last theorem I showed you about products of endofunctors was with respect to the category of sets in a topos. So in other words, one of the universes in your topos. If you want to consider taking products of endofunctors for more general sorts of categories, one's going to need to know something a bit about the categories other than that they're just co-complete. You'd like them to be built up, you know, in some typically kind of locally presentable kind of way. And I wonder whether this kind of plump W types and whisk would give rise to an interesting constructive version of accessible categories. And it's not something that we've thought that much about yet. But one thing I did want to say is that, at least personally speaking, where the avoidance of successor ordinals and zero ordinals came from for me was just because I was used to using this, what I've called inflationary iteration style, when I was using so-called size types in Agda to prove various things. Very fun sort of thing to do. Agda size types don't force you to do things in this kind of way, but they work out nicely if you do them in that way. So it was suggested by that. You can prove lots of things using size types in Agda. Unfortunately, you can prove anything at the moment because it's still sadly true that they're logically inconsistent in the current version of Agda. But just because they're inconsistent doesn't make them not useful. And actually what people do with size types in practice most of the time is sort of on the dual of the kind of thing I've been talking about, namely on the co-inductive size. And it's certainly the case that one could do a dual version of my first theorem. So in other words, build up the sequence and at each stage take limits instead of co-limits, and then at the end take a limit. And that would be giving you a final co-algebra if that limit is preserved by the endofunctor. That's just simply the dual of the first theorem that I told you about. And it might be that the things I've been talking about here could be usefully applied. Again, it's not something that we've yet thought very much about to get results of our final co-algebras. And just to finish, I just want to say that whilst I am using this whisk here, I don't think it's necessarily the only way of doing things. We're doing things this way because it works. But of course, I mean, if you use Agda's size types, it's not, even though they're inconsistent, it's not that there's some use of that particular whisk axiom hiding away behind what they're doing there. It's just not quite clear semantically what is going on with Agda's size type. So, and with that, I think I'll finish and take any questions. Thank you very much.
Thanks for the talk. That was super interesting. Okay, we have plenty of time for questions, so I think we'll start with Torsten. He was the quickest off the mark. I'll just.
Oh yeah. Okay. So previously, I was tried to ask something, but I couldn't say anything. So, but anyway, thank you very much for your talk. It's very interesting. I'm also reading in the moment a paper which you mentioned already, which is related and which made me think about this stuff as well. So I have some comments on the last point. So if I think about it, I mean, so yes, so I would like to have this as well. That like a W type should be a co-limit, and that's that's a misfit in type theory in the moment, right? So that we cannot, and we'd like to have this, and certainly this application to the quiz is very natural and very, very sensible. So I wonder a little bit whether I like this whisk. First of all, to me, it's like the dual, in a sense, the dual of a sub-object classifier. It's like a super object classifier, because you look at all the quotients, you quantify over all the quotients of a given type, and this is what you call the covers, right? So in a way, you have a representation of all the quotients, where for power, I mean, a power object, you have a representation of all the subsets. So in this sense, it feels very impredicative.
Yeah, and that's right. And I think it came up first, mostly to do with thinking about how toposes would model various kinds of set theory with replacement and so on, where you want some hold over how many quotients you've got, as it were. So yeah. Yes, so it's exactly like that. Yeah, yeah.
So here's a point. So if you think about this container example, I mean, well, no, I mean, yeah. Let's say the positions will be just natural numbers, infinite. Yeah.
Yeah. I just should say one thing about containers, right? You definitely don't need anything that I've said in order to construct the initial algebra for a polynomial endofunctor, because you can just do the final co-algebra, which constructs the possibly ill-founded trees, and then take a well-founded part. So that's not, you know, the existence of initial algebras for polynomial endofunctors constructively is not one of the theorems that we would say is a new theorem, right? It's but only when quotients enter that. But
the point is that this W type should arise as a co-limit of this functor, or I mean, as this container, right? And that's the point here. Yeah. So here's an observation: if we are in the setoid interpretation of type theory, we do have certain choice principles. I mean, choice principle for everything which has a trivial equality, so to say. Yeah. So, for example, natural numbers. So in the setoid model or groupoid model, which is very natural, I do get certain constructions, but I suspect that I don't get whisk. Yeah. So
yeah, maybe so. I mean, that also reminds me of the reason why, if I think I'm right in saying this, but I haven't really seriously thought about it, but I think whisk would be true in the realizability topos for the same kind of reason that you say, that secretly you have this intentional representation of things, you know, in terms of indices, and you can do stuff at that level. So it's not dissimilar to the setoid kind of thing. Yeah. Yeah. It's pairs rather than setoids, but yeah. Anyway. Thanks.
Okay, so next we have Paul Taylor. Paul, please go ahead. You should be able to unmute yourself. Paul, are you there? Yeah.
Yes, I'm here. I'm here. Yes.
Hello, Paul.
Okay, so there's an open-ended discussion that I'd like to join at the end of the session, but I've got three simple points I wanted to make. Firstly, I don't recall the definition of plumpness that you gave. I don't recall that I said that. I do recall that Mike Schulman independently discovered plumpness in his version of the Conway numbers in homotopy type theory, and in particular constructively. They were definitely the interleaved reflexive and irreflexive orders in that case. So that's
yeah, and I think now you say it, I think you're spot on there, because I think I got this via Mike Schulman.
Yes. It might,
who references you. Well, is that definition of plumpness buried in the JSL paper?
It probably is. It is 30 years ago I wrote it.
Yeah.
Or published it.
Okay. When we write this up, I think we'll give a little bit of credit to Mike.
I'll check it. Well, I have been thinking about this subject again. In fact, this week I had a good discussion with Tomo Osterlund yesterday, trying to match up what I did with his at least first attempt at doing a dual version. I've learned some things from that conversation, which I'm not going to say now because it's still current. There is a new version I just uploaded this morning of my new well-founded co-algebras paper that's on my website at paultaylor.eu/ordinals, although it's not significantly different from the version of August last year. Now I was going to say something else, but I've forgotten what it was. I'll say, if I remember the other point I was going to make, I'll say it later on. But I'd like at the end to have a more open-ended discussion about how to construct things like free algebras with infinite free algebras with equations that you were talking about a while back, and also there's the proof theorists make serious use of ordinals and recursion, things like cutting elimination, and it would be nice if categorists had something to say about that. I mean, it does seem to me that I have strong opinions against classical ordinals for a number of reasons, but one of them is because they seem to be so almost literally narrow-minded that they're not. It's not taking natural account of the inductive structure in something like a type theory or whatever it is.
I should say, by the way, one I forgot to say this. I meant to say it during the talk. The one thing about ordinals that you could do constructively that we just don't seem to need at all here is extensionality. So we're not interested in whether the sizes are extensional in the sense of two elements being equal if they all have the same predecessors.
Well, extensionality is interesting because extensional well-founded co-algebras are initial segments of the initial algebra.
Yeah.
So when I first
I don't doubt it. It's just I'm saying that so far we haven't needed.
I can see that why it wouldn't come up in what you used at the moment. But what I imagined a long time ago was that if you wanted to construct the initial algebra for something complicated, it could conceivably be simpler to construct the extensional well-founded co-algebras and then you'd see how the whole thing was built up of parts of it.
And that certainly seems to be true for humble W types, doesn't it? Because
Yes,
the final coalgebra is very easily described. So because it is, as I think we were discussing, that those polynomial endofunctors preserve connected limits. So you get to the final coalgebra at the countable limit of the iteration starting at the terminal object.
Yeah.
Yeah.
Yes. Your iteration of functors. I did, tease you with an idea about those, presenting those in terms of vibrations, and the very final pages of my book.
Yeah.
That was my third point. Yes.
So it looks like we're going to have an interesting discussion after the talk.
Yes.
So next person is Steve Vickers. Please go ahead, Steve.
Yeah, if you have no choice at all, you can still get initial model theorems if you have some topology to help you. So if you replace categories by toposes and functors by geometric morphisms, then as long as the topos, if you've got a topos with an endomorphism, an endomap, and the topos is local, so it's got an initial object, then you can apply pretty much the usual construction, and you get an initial model. In other words, that the classifier for the algebras, the F algebra, is again local. So that is a sort of you hardly need any foundations at all to get that much, and I wonder how much one can connect the two different approaches, that topos theoretic one on the one hand, and the more doing without topology in the kind of approach that you were taking.
I'd hope that one could, right? Because they're sort of topos is sort of like geometric logic or whatever, and yeah. So yeah. But I take the point. So topology could help, as it were, cut things down sufficiently that you didn't need some choice principle at all to
yeah. So in topology via logic, that's how I was solving domain equations.
Yeah. Thank you.
Next we have Gordon Plotkin. Gordon, please go ahead.
Hi, Andy. So I just wanted to ask a question which Paul will ask you, but I won't stay for the discussion. So how about free algebras, some suitable collection of equations?
Yeah, so we can do that. We actually, if you look at let's get the reference.
Okay.
Sorry. I see. Excuse me a moment.
Sure.
It's a defect of the application, not.
I can just believe whatever you say without seeing.
Yeah, right. So that paper on the archive. So Marcella and Sean and I, we do indeed construct pre-algebras for infinite tree equational theories in a setting where we've got whisk around. So constructive plus this whisk principle. So it's not exactly a corollary of the theorem I showed you in this talk, but it uses the same techniques. So it uses the notion of size, and you build up a size index collection of things and take a co-limit, but it gives you the initial algebra. So we can do that using related methods. But again,
okay,
I take the point that I mean, it is using this whisk axiom, and I understand why people kind of look slightly askance and think, can't you just do it some other way? And in certain circumstances, maybe you can, right? I mean, as Steve was saying. Anyway, yeah.
Yeah, but I'm in the useful camp, so I don't mind about whiskey.
Yeah, yeah, I don't. Yeah, well, exactly. Yes, yes. I mean, it's true, right?
Okay. Okay. Thank you. Thanks.
Thank you. Nice to see you, Gordon.
Nice to see you too.
I think we have time for one more question. Stefan Milius. Stefan, please go ahead.
Hi, Andy. Thanks for a very nice talk.
Hi.
I have a question about the result you mentioned briefly at the last slide about terminal coalgebras.
Oh, yeah.
So you've got the standard dual result for functors preserving limits of kappa op chains. But in classical set theory, you also have this result by James Worrell that if you have a kappa accessible functor on sets and you go along the chain for a kappa times 2 steps, you get the terminal coalgebra. So that might be interesting because you've got lots more functors which are kappa accessible and preserving kappa limits. Do you know anything about this here?
No, not at all. But I was hoping that somebody would tell me some stuff. So that's really excellent. Thank you. I mean, I admit my ignorance in this area because I've never really sort of delved into what's known. So you've just told me something very interesting there, right?
Okay.
It's certainly, you know, preserving all kappa limits is a pretty strong thing to ask, and it would be much nicer to have a weaker thing. Yeah. So, yeah. Good. We should see whether it works.
Okay, I think we're out of questions. So before I stop the recording, I'm just going to get everyone left to unmute themselves so we can give Andy a round of applause. Okay, so I'll stop the recording and
most humans are capable of much.
I'll mute everybody. So I'm going to stop the recording now. You're welcome to stick around and join the discussion. I'm sure it's going to be fascinating.